Good day and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Anton Karamyshev. Anton received the bachelor and master degrees in applied mathematics and physics in 2021 and 2023, respectively, from the Moscow Institute of Physics and Technology. He is currently working toward his PhD degree in telecommunications at MIT. Also, he is a researcher with the Wireless Networks Lab of the Institute for Information Transmission Problems. His research interests include the future wireless networks, namely 5G, 6G, and state-of-the-art Wi-Fi networks, applied to the URLC and industrial scenarios. Today, he will present us results of his research recently published in the Transactions on Industrial Informatics journal. Anton, the floor is yours.
Yeah, hello once again. And first of all, and thanks Vyacheslav for the introduction. And today I'm going to speak on the enabling industrial Internet of Things with Wi-Fi 6, or to be precise, how to optimize Wi-Fi such that it be good enough to use it in industrial environments. And probably then first and extra note, if you have any questions, please use chat to mark about them, or feel free to use the chat about the notes. I hope in the end we can move on back to your questions and I will manage to answer them. Thanks. First of all, to get started, I would like to give an extremely short piece of background information. In recent years, there has been a rapid development trend of industrialized systems, also known as the Industrial Internet of Things, which promises to connect manufacturing, safety equipment into a single conversion network. It also promises to exclude humans from their interactions in factory pipelines, which means that we aim to build in fully autonomous systems. And applications for IoT include the automotive, oil and gas industries, the agricultural sector, and so on. But in this speech, and which is based on the industrial project with non-disclosure production of equipment, we will target mostly automotive applications, but I hope that my conclusions and my remarks will be applicable to the most of the listed scenarios. So, Industrial Internet of Things needs to connect multiple devices using either wired or wireless. And providing wireless connectivity for Industrial Internet of Things is both a great opportunity and a great challenge. The first one, the opportunity comes from low installation and maintenance costs, as well as from enablement for mobile and rotary equipment. For example, it can be rubber arms or actuators. They can rotate, they can move across the product line, and so on. From the other side, the challenge arises from the strict, and I should say extremely strict in quality of the service requirements, which are hard to satisfy in wireless networks of the present and the near future due to the unpredictability of the wireless medium. So it is a kind of choosing between virus and wireless, but for the virus, we should solve a lot of problems regarding the quality of the service. Yeah, and to begin, actually, I should describe a core industrial Internet of Things and scenarios, and it is usually a closed loop of a data exchange between some controller to multiple responders or vice versa. It can be commands from the controller to responders which contain coordinates and some other technical stuff, and then status reports from responders to the controller, which also contain some coordinates, measurements, and so on. As I already highlighted, the main feature of Industrial Internet of Things scenarios is and applications is strict in quality of the service requirements. Usually, the period of data exchange and latency should be less than several milliseconds, and reliability should be more than 1 minus, let me switch to the marker, 1 and minus 10 to the power of minus 6. It is usually expressed in the number of nines, let's say 6 once again. And probably we should target the scenarios and when the number of devices is extremely large. For example, we account the real production online, and when per single access point we aim to connect more than 100 of devices. And also, apart from the latency, we also target to decrease jitter significantly because synchronized behavior of the robot arms is required to operate in the production lines. And the described set of strict and quality of the set requirements is actually a quite new challenge for wireless networks. I mean, starting from 5G probably, and a vehicle for the future wireless developments. So, and one of the possible wireless technologies for Industrial Internet of Things is well known to you, Wi-Fi. And Wi-Fi evolution, namely about 3 decades of its development, has turned Wi-Fi into pretty much versatile tool for residential use cases. However, Wi-Fi was not initially intended for use in industrial systems. So then the benefits of Wi-Fi usage in the industrial setup is rather questionable, which we should explore in this talk. But luckily, Wi-Fi of the present and the near future is theoretically capable of delivering low latency, high throughput, and reliability at the same time, I hope. But a comprehensive analysis of Wi-Fi mechanisms and joint optimizations of Wi-Fi mechanisms, once again, is still required to use it effectively to enable the IoT vehicle in Wi-Fi functionality. And I should then say a bit about other works here, but generally the existing works fell short of satisfying this need of comprehensive analysis and optimizations, because researchers usually do not dig into details of the spec. They just use the devices from the shelf. They do not explore features that we use, and the researchers usually do not really interested in benefits that they can obtain from the Wi-Fi if they fine-tune it pretty much a little bit. So to get into details and analysis of this and Wi-Fi, of this new set of Wi-Fi mechanisms, I would like to formulate the problem statement. Our general target is to increase the system capacity, in which we measure in the number of devices, I mean responders here, by selecting and tuning Wi-Fi mechanisms within the strict set of quality of the service requirements. For example, if you look here, we aim to increase the number of devices in the network. It is expressed here by n and as a number of NBSSs, which is just the networks for the simplicity. Under the constraints of the quality of the service, the first one is packet loss ratio, which just the common metric of packet loss. And the second one is the cycle duration, which can converge the whole data exchange cycle into a single latency requirements, and it is pretty much popular key performance indicator for the industrial systems. Yeah. And we aim to tune somehow the set of Wi-Fi mechanisms and maybe modulation and coding schemes, synchronization and parameters, and so on to increase the capacity. The similar optimization problem can be formulated and vice versa. For example, if we keep the number of devices constant, we may aim to decrease some of the quality of the service requirements. For example, the duration of the communication cycle, or increase the reliability, which means that we aim to decrease the packet loss ratio. Yeah. And moving to the second part of my talk, I would like to start from the describing the scenario in a more detail, and because my conclusions will rely on these unique features of the industrial setup. And first of all, we assume that we consider fully capable Wi-Fi 6 devices, which is 802.11ax. I guess it is more than 5 years from the release of Wi-Fi 6, so we can pretty much assume that this type of devices are available in the market freely. Then we consider a closed loop control cycle between the controller, which is here, and a lot of responders via access point. I mean, we starting to send commands to responders from controller. It is stage 1 to the access point, and then access point and forwards such commands to responders. I mean, it is stage 2 in the picture. And when responders want to send status reports to the controller, they perform such transmissions and vice versa. They send this status reports to the access points. It's stage 3, and then the access points or the access point forwards such aggregated set of reports into the controller. We actually consider short packets, and because in such industrial data exchange cycle, we don't need a lot of information. We just need some doubles and fours. We do not intend to transmit in high quality video. So the packets are usually short, about of 100 of payload, but the number of devices isn't quite high in the network. So the overall per network load is quite high as well. Yeah, we consider such geometry. I mean, just imagine some industrial hall that are divided into several networks, and per each network, which is depicted by the colored square, we use the single access point and a lot of responders. Due to frequency and scarcity, several networks may share the same channels, and it may not produce some interference, but we will solve these problems later. And some technical stuff about the devices, we assume that it is that access points and have 8 omni antennas, stars and have only 2 omni antennas. Access points are mounted on the ceilings of the industrial hall, which is about 3 to 4 meters and so on. And pretty much the last one here, we assume that responders are always located inside the Khorov square. I mean, we do not consider internal BSS roaming. It is quite strange and complicated topic to evaluate and to optimize here. Our main simulation tool is NS3 with a model channel according to GPP doc and use the full description of the industrial setup. So because this document is quite popular and justified, I hope that our results are quite well applied to the realities as well. And let me turn to the experiments itself. In the next slide, I will describe a set of short experiments, and probably from each of the experiments, we will derive a kind of the conclusion or a lesson, which we then are going to aggregate and to formulate the complicated set of mechanisms optimizations, and which we then in the end will evaluate, and we will try to get some gains and let me say large-scale conclusions from such of the industrial environment. Yeah, I would like to start from the basics. Probably every one of you knows that 802.11x introduces trigger-based channel access, which is probably then clear definition for the scheduled channel access in Wi-Fi, and we can even deprecate the classical enhanced distributed channel access of the Wi-Fi because we pretty much clear understand that when the number of devices is high, I mean responders, EDCA is a bad choice, because we will experience a lot of collisions and the overall performance of our network will degrade. So then the first move to the optimized solution is to use scheduled channel access and to disable EDCA completely. Also, to do it, we probably will need some tighter synchronization feature. I mean, we shouldn't work with a synchronized clock on the access point, the controller, responders, and so on. And on Wi-Fi of the present already provides a lot of tools to synchronize the clocks, even with the external coordinator. I mean, it is on time synchronization function or on time advertisement and so on. Then, if we synchronized our transmissions and we use the trigger-based channel access from Wi-Fi 6, I mean, we probably want to use something like ODMA or something like aggregated transmission. And speaking about aggregation, it is then classical of Wi-Fi. Wi-Fi offers aggregated MPDUs and aggregated MSDUs from Wi-Fi 4. And then classically, we used a MPDU because of the option of independent decoding of the packets, and it is usually provides slightly better reliability because our transmissions are quite long, and we hope that we can decode some of the MPDUs in A MPDUs because because in channel and fades, for example, and broke only a part of our transmission. But industrial comments and status reports usually of a small size. I mean, and once again, it is about 100 per payload. And the number of devices is high. And so from this fact, we can notice that the first variant aggregated MSDU saves about 20 bytes per MPDU compared to a MPDU. And so speaking about overhead, a MSDU overwhelms then the second invariant and frames to or vice versa, only a tiny reliability win. And once again, winner probably will win anything because the transmission are rather short. So the second conclusion or a lesson here that we should use aggregated MSDU to reduce overhead in general, and we should use aggregation to reduce channel access-centered preambles overhead. Then I would like to turn to the wide topic of MIMA and multi-user MIMA and the sounding. Speaking about industrial environments, the channel quality changed rapidly because a lot of metal reflectors. So we should perform sounding procedure quite frequently to extract the actual state of channel and exploit it. And when, for example, we use or we choose MCSs or we use beamforming and so on. Without such of frequent sounding, we probably fail to leverage any MIMA or MU-MIMA benefits. But in our industrial setup, the number of devices is quite high. So sounding for multiple devices is expensive, yet the data and the packets are short, which means that we do not really win when we choose a higher MCSs because, for example, our packets may already fit into a single OFDM symbol, and this is a kind of effect from the quantum mechanics, so we already approach to 1 quant of our transmission time. So the question is, do we really need MIMA? Because the overhead is likely to diminish the potential gain. To answer these questions, let's consider that the periodic frame exchanges with some experiments. It is chosen as 500 milliseconds and here, and we would find the MCS that ensures our packet loss ratio less than 10 to the power of 1-6, and we will calculate channel occupation at time as a sum of transmission in general and channel measurement durations per all tasks that we perform on these MCSs. And we will compare our MIMA setup versus only Omni setup, without any spatial streams and so on, and precoders as well. So here you can see the results. Then left figure is applied to the P2P transmissions, from the controller to access points. And we transmit here a quite large packet, and because we aggregate in several packets into the single one and forward it. And in the right, you can see the same experiment, but for one-to-many transmission. And for example, when we transmit multiple packets from the access point into our multiple responders. And actually, probably you can already scan over the labels. And here, let me describe one feature, or I probably explain the notation of such handbars. And when it is 1 to the 2, it means that one period of transmission, I mean 5 milliseconds, is used with twicely longer period of unsounding. It is 10 milliseconds here. So you can calculate, for example, here, when it is 1 to the 100, then the period of unsounding is in 500 milliseconds. So, and actually, when we compare the results, we can see that gain from the MIMA is quite lower in the first set of experiments. We can save only about 20% of channel occupational time. And this is only one communication stage in our cycle. So the overall gain will be much lower. And also in our experiments, we do not account any losses during channel sounding procedure. So the gain is likely to be less than 5%. And when we look at the one-to-many transmission scenario, I mean here, probably always our Omni setup will outperform the MIMA setup because the overhead for sounding of multiple devices is quite high. So you can see that these dashed bars a lot. And we actually go to our conclusion and here that controversially, but using Omni transmissions seems more, much more wise choice than using a widespread MIMA in our current industrial setup. And yeah, to answer my previous questions, it seems that we don't need any MIMA and sounding due to too high overhead of the sounding. Yeah, but I would like here to note that we do not deprecate any reception side MIMA, I mean equalizations, and so on. Because, of course, if we talk about devices with multiple antennas, some equalization algorithms are extremely fruitful to enhance reliability. And also, when we deprecate any sounding content on MIMA, we should find a way how to choose MCSs, because we fail to exploit frequency selectivity. We do not have any channel state information, so probably we should use one MCSs per each cycle or pitch. Or, for example, 2 MCSs for downlink and uplink, or something like that. And actually, speaking about channel selectivity, as I have, as I had said, without an MIMA and an sounding, the scheduler has no SNR information at all, so we cannot exploit frequency selectivity. We should use the same MCSs at least in per downlink and uplink, or at least in per downlink and uplink and bandwidth and power combination that covers the requirement of the reliability. And such a set of MCSs will determine the schedule of the package generation, or actually and vice versa. When we target to increase the system and performance under the extreme lower quantile of bad events in the channel, we should not target this channel. So without frequency selectivity, we should always choose this. We should always choose MCSs with in mind of such bad tail of channel quality events. And here I would like to give you two notes. Once again, the first is when we operate in a narrow channel, it means that we should work with a much more channel quality fluctuation. I mean, the dispersion of the channel will be quite higher compared to the wider channels. And in uplink, vice versa, using of narrow channels means that we will experience much higher power spectral density, is about past 3 of decibels per channel and with duplication. So we will experience better reliability. And moving to the experiments itself, in the left, you can see the distributions of the SNR in the downlink, and in the right, you can see the same distributions for the uplink. And we can see for the downlink that because we use the same power spectral density in here using of narrow channels, I mean RUs here applying to OFDMA, means that we will lose more than 10 of decibels, which is more than 3 indices of MCSs, and it is a lot of time. So probably in downlink, we should use wider channels to account such reliability losses. And vice versa, in uplink with equalization, the narrow channels provide much more better reliability thanks to higher power spectral density, as well as if we use narrow channels in OFDMA, and we work with synchronized transmissions, we will boost our latency also. And once again, about the downlink, actually, if we compare our downlink of DMA setup and the transmission of aggregated packets into a single frame, for example, like a broadcast or a groupcast, we can notice that using of wider channels also reduces channel occupation at time. For example, if we compare a downlink of DMA here and a groupcast here using aggregated MSDU, we can see that a groupcast requires twice less times than a downlink of DMA. So if we use wider channels in downlink to deliver one-to-many transmissions, we will increase both reliability and latency. And it is quite unexpectedly, actually, because groupcast and broadcast are not really used nowadays. I mean, in such a set of scenarios, but actually we should. And one note here, thanks to the choice of aggregated MSDU, we are able to use groupcast here, and because the groupcast is deprecated with a MPDU because of addresses issue. And the second note here that with groupcast, we should account the issue of the acknowledgements, but I hope I will cover it in a few slides. And in uplink of DMA, we already agreed. I hope that we should use it, and when we transmit our packets from multiple radio lines to a single one. But here, then baseline of Wi-Fi 6 requires the knowledge of a buffer at any start to trigger to start uplink of DMA transmissions. And by default, it is used with a quite long buffer status report and poll procedure. I mean, we transmit PSRP trigger, we transmit cost analysis with buffer markers, and only then we can trigger the actual uplink or domain procedure. But notably, we can use some other Wi-Fi features like the spec or quality of the service stream classification service with cost characteristics elements, but it is actually from Wi-Fi 7, but it is okay. And the access point will know in advance about the packets in the stars, in the responders, and the access point will be able to trigger the transmission of such packets without any additional delay and overhead on the polling of such station. And actually, regarding the retransmissions and acknowledgements, if we perform the previous set of experiments, I mean, use some periodic transmission within a period of 5 milliseconds in a downlink, and we will we wanna find out how beneficial Wi-Fi retransmission on the macro level, I mean. And we can experiment, I'm sorry, the pictures are, okay, I guess you will understand without English and language here. It is my bad. It is the distribution of the channel it is complementary CDF of the packet and the time delivery. So, and for example, if we look at the red line here, 100% of the packets will deliver here, and it is in microseconds. But if we look at, for example, MCSS 10, we can see that if we do some retransmissions, our tail will indicate us that some packets are successful within second, third, or the fourth retries. I mean, these dots here. But the gain actually is then quite lower, because if we fail in the first transmission attempt, we are highly likely to fail in the second transmission attempt, and the third, and the fourth, and so on. And the situation doesn't change if we consider the classic Wi-Fi retries, I mean, with Lyakhov and so on, and or then blind retries. For example, here, when we try to send our packets just in 5 times, then the gain is still quite negligible to consider. And it works when we perform the retransmissions using the same MCSs as our first try. But why do not decrease our MCSs on the retries? Because of the jitter. First of all, we cannot predict any failures. So we should introduce an extremely long jitter buffer. And the reliability gain isn't quite small to develop and introduce such a jitter buffer. So probably we should use the reliable MCSs in the first our try. And this is a solution here. But if we aim to deliver our data from the first try, do we need acknowledgements at all? And probably we don't, and because acknowledgement also will introduce a lot of overhead, because and once again, our data and the packets are quite small, so additional sieves and eggs will add a lot to our communication cycle. So if we deprecate any retransmissions, and if we will use no egg policy, we will able to cut down our communication cycle a lot. So yeah, and once again, if we get rid of any retransmissions and acknowledgements, we are able to use broadcast or groupcast, and when we transmit in the packets and one-to-many. And probably the last mini experiments here, it is a note about interference. As I said in the beginning, our networks may share the same frequency channel, but let's look on the thinner degradation when several networks are transmitting simultaneously. And if we look here, it is more than 40 decibels. So probably if we remember our reliability target, we should then look here, and it is minus 20 of decibels. We are clearly not be able to deliver any data here. So we should avoid interference and not mitigate in such industrial setup with an extreme requirement for the reliability. So the conclusion here is that neighboring BSS shall transmit in either non-overlapping channels or using non-overlapping time intervals. And this idea is in fact simplified, coordinated TDMA or coordinated OFDMA from Wi-Fi 8, which is under development, by the way. Yeah, and this is a conclusion stack. I mean, it is just these lessons or on conclusions, but on combined in the one slide. I probably will give you 20 seconds here to get some water, and I will be right back soon. Okay, I guess I will go back to the question in the end. Yeah, and here just in conclusion, and now we will try to apply such set of conclusions or lessons learned from mini experiments to build our complicated in a right way and solution for the whole closed loop data exchange cycle. Yeah, and this is a kind of table which formulates the three of the solutions, how to organize a closed loop of data exchange in the described industrial setup. First of all, let's consider something like Wi-Fi 4 setup, because a lot of researchers still use it as Wi-Fi behavior and complains that the performance isn't quite bad. So it is our bull baseline. Then we will look at the retina baseline when we use Wi-Fi 6 functionality, but some of the stuff and the features are not optimized still. For example, we use downlink of DMA instead of groupcast when we transmit one-to-many, and we use X with the classic and Wi-Fi retries and so on. And finally, I would like to show the results for the green solution, which is Wi-Fi 6 optimized, which I try to advocate for you here during my talk and in our recent paper. So we just perform the described in the previous slide modifications. For example, we once again use trigger-based channel access for all stars, and we do not use EDCA and we do not use EDCA in the phone controller even. We deprecate acknowledgements. We build a scheduled and packet generation across the whole set of NBSSs that share a single channel and so on. And actually, I would like to note that the optimized solution, because it tries to deliver all the data from the first try, it also achieves almost zero jitter. I mean, our jitter only can experiments from time synchronization issues, I guess. And that's all. And you can see in the picture representation of the whole cycles for the red solution here and for the green solution here. And you can see that if we get rid of X, for example, here, 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 and here, we can save a lot. We actually may get rid of buffer status report Polymer procedure and saves, and it will save us a lot of time and so on. And just a tiny example on how such modifications affect our communication and cycle duration. For example, if we start at Wi-Fi 6 and baseline, and we just switch on features. For example, we get rid of buffer status report procedure. We get rid of X, and we will switch from a downlink of DMA into groupcast. We will reduce our communication cycle duration significantly. Probably it is. Yeah, it is 1/2 here equally. And you can see that such a schedule or a calculation can be performed per MCSs and per each number of the devices in NBSSs. So our additional parameters, I mean, additional to the set of this set of free solutions will be MCSs and time synchronization parameters, I mean, packet generation schedule. And so if we, for example, assume that only two MCSs are used, the one in downlink and the second one in uplink, we can calculate the whole schedule for the, for the all set of MCSs, and based on some gathered statistics, we can choose the MCSs that will ensure our reliability target. Then we can configure our devices, because we are in our industrial setup, and we probably can change and then can change some parameters for our device at any time, so we can just make it and work with a different schedule with it, different MCSs. For example, if we want to increase the number of devices or decrease the communication cycle duration. Yeah, and we still target to keep packet loss and ratio below 10 to the power of -6. And here I would like to present the first set of results. For example, if we target to keep packet loss ratio below 10 to the power of -6, and we want to keep cycle time duration less than 4 milliseconds, we aim to increase the system capacity. And you can see that if we increase the number of devices in the network, we clearly should use higher MCSs, and will degrade our packet loss ratio. So because of it, all the curves are increased in the right side of the plot. But what most importantly in here is that our green and proposed solution outperforms on both baselines, and to be precise, if we compare this dot and this dot, we are able to achieve more than 2.5 capacity increase, which is a lot. I mean, per a single Wi-Fi 6 router, we can serve more than 60 robots or responders, and which is quite a significant result for the industrial deployments. Then the second set of the results describes the situation when we keep the number of responders in the network, but we will try to decrease the communication and cycle duration. And here, once again, we can see that our green advocated solution managed just to achieve twice lower communication and cycle duration. And what most importantly in here, if you use CDCA and baseline, it is clearly fail to deliver any reasonable values of the packet and loss and ratio. So probably researchers shouldn't use any DCA, and for now in industrial setup with a periodic or cyclic traffic. And the last set of the results here, it is devoted to the question how to choose channel width. For example, we can use a 40 megahertz channel, but place two networks inside it, or we can use two different, orthogonal 20 megahertz channels and place one network in each channel. So, it is actually a different set of results, but okay. It is devoted to the question how to choose channel this. And clearly, if we use wider channels, we will able to achieve smaller communication cycles. For example, here, if we use 116 megahertz in a channel, we can achieve slightly more than 1 millisecond communication cycle duration for 50 responders in one BSS, but when we are using 20 megahertz in channel, we will able to achieve only 3.5 millisecond communication cycle. But actually, do we need 1 millisecond communication cycle? Probably not. So because of it, I and my colleagues in the paper will derive this spectral efficiency metric to measure how effectively we use channel and time for our capacity in the system. And if we calculate such a value for this set of bars, we will see that we will achieve more spectral efficiency when we are using narrow channels. This is because the fact that when we are using wider channels, 1 and 16, for example, some of the transmissions of short packets are already fit into one OFDM symbol. And also when we are using wide channels, we will lose power spectral densities, so we have to choose MCSs lower. It will increase our efficiency too. And because of it, until the extremely low cycles are out of our interests, the use of narrow channels, 20 megahertz to be precise, without TDD is the most favorable or efficient in ways to orchestrate our frequency organization for our industrial setup. And it is actually quite interesting because the last Wi-Fi generation tried to boost our throughput values by increasing channels, by applying MIMA with a lot of spatial streams. But here in our industrial setup of the present or the near future, we see that we should do things that's controversial with the previous direction of Wi-Fi. For example, we should discard any MIMA and sounding, and we should use narrow channels and so on. And it is quite an unexpected result, at least for me, when we performed on such a set of simulations and so on. And I hope it is nearly the end of my presentation. I would like to give you a short note on other technologies' performance. Of course, it is really debatable topic, and I do not want to dig into details, but based on the results from other papers, our Wi-Fi setup is able to achieve more spectral efficiency than the other technologies. Because of, for example, if we compare our setup, which is here, to the setup from these papers, the authors here evaluate only random downlink traffic, and of course they do not apply any optimizations for the cyclic traffic, and the performance of Wi-Fi is quite bad here. And also, if we compare some other small stuff, let me say, and which is use 802.11.5, but I tried to I am unspoken now about virus Sharp and virus HP. As these technologies try to build different MAC layer functionality under 802.11.5, and these technologies are targeting much lower communication and cycle durations, but they do not exploit any of the modern and Wi-Fi features. For example, channel access stuff with trigger and frames and so on. The work of equalization is hardly possible here and so on. So the spectral efficiency here is also lower. And I do not want to speak about the 5G and the 6G here, but according to the results from other paper, the setup based on the fifth generation is a similar environments. I'm highlighting this in the paper. The setups which are based on the fifth generations are worse than our optimized Wi-Fi here. So probably we should use Wi-Fi for our industrial setups because Wi-Fi devices are extremely cheap, extremely, I don't know, well known. You can easily find any devices in the market, but to build any private and 5G network, you should do a lot, and to build as a network of such devices, you should do even more. And yeah, here are the conclusions. I guess I do not want to bother you by any description of the precise conclusion, but the main one is that today's Wi-Fi is already suitable for industrial Internet of Things scenarios, yet it should be tightly optimized and fine-tuned, let me say. But actually, I want to highlight here that any changes that I describe today are working within as the same standard of Wi-Fi 6 functionality. So we do not we don't need to change any of chipsets and so on, just the application stuff. And how to even more boost the performance or extend applicability of the advocated solution. For example, we can focus on lighter sounding sequences. And for example, if we are able to perform implicit sounding for multiple devices at the same time, probably it will enable the gain from the MIMA, at least I hope. We also can integrate the header compression technique into a Wi-Fi stack. I mean, even compress MAC header as it done in 11AH. We also may introduce the multi-link comparison from Wi-Fi 7, but here, and personally, I'm not sure about the trade-off in terms of spectral efficiency. We should evaluate it properly. And also, maybe we can mitigate interference in a more wise way, for example, with a multi-API coordination feature from Wi-Fi 8. We can also enable internet-based roaming, which is the important topic in 802.11bn currently. So a lot of the question can be considered. And I hope you will find this and set of topics and useful to explore. And yeah, finally, if you want more details, you can refer to the recent publications of me and my colleagues, which have been published in Transactions on Industrial Informatics here. And this is a preliminary paper that will describe some mini experiments that also had been presented here today. And I guess that's all. Thanks. I'm going to the questions now. So if you have any, please mark something in the chat. I will be happy to answer them. So let me go to the first question in the chat from Artem. Yeah, and here, what Omni means, do you consider the gain from equalization of several receive antennas? Yes, I mean, Omni means that we do not use any precoding and we transmit using one spatial streams. But we can use receiver side MIMA, I mean, equalization, MMSE, or different equalization techniques. Then the next question from Vyacheslav, which precoder is used for MIMA
Sorry,
transmission?
maybe missed the previous question about controller.
Oh, yeah, I'm sorry. Wine controller, yeah, I see. The first question is from Artem. Wine controller is not connected to the access point by wires. The short question is isn't because the controller also can move. The description of the scenario will be given by our non-disclosed industrial partner. So it isn't what it is. The controller in general can move too, and it can be a robot.
Maybe further question, is it a common scenario? So maybe the scenario of your industrial partner is so narrow that it's not the usual case.
Okay, we can see the similar setup. I mean, within 4 stages, within moving stations, including a controller in other papers. So I assume that it is that this scenario can be applied into reality. Yeah, I'm not sure about the frequency. Let me say in real life of such a scenario of applicability, but it is what it is.
Thank you.
Yeah, I hope on question 2 is closed now. I hope. Please confirm. Artem.
Yeah, for Omni, you already answered during your talk.
Okay, the next question is from Vyacheslav. Which precoder is used for the MIMO transmissions? We used simple MMSC without any modifications and so on.
But as I understand, you have MSDU transmissions which are for different users. And to build a precoder, you need to select some particular user or not.
I'm sorry, a precoder. We do not use any in the precoder when we're using Omni transmissions, which means that we use the trivial matrix when we transmit the signal. So, and when we do not use MIMO here, let me change the slide. Yeah, here. We do not use any precoding when we use Omni transmissions.
That's clear. My question about two spatial streams.
Actually, I don't know, but perhaps you know our Codno base, and it is the default one. I can check if you wanna.
No. My question is not like, do you select some zero forcing, block diagonalization, and solve precoder? My question is, I don't quite understand. So you have am I right that you transmit AMSDU, and in this AMSDU, MSDUs are distant to different stations?
Here, actually, and when we working in one-to-many downlink of DMA transmissions, we just use OFDMA, but we can use one or two spatial streams in each RU of a downlink of DMA transmission. Is it clear now? Without any MU MIMO in its classic way.
So you use OFDMA here, and in each RU you transmit to one station or several stations?
One. Just one. Да.
But why do you use AMSDU here?
Why not?
I don't remember. In this case, you have different AMSDUs in different RUs, or you have one MSDU for the whole bandwidth.
Okay. When we transmit in one-to-many, I mean, it is stage 2. Actually, let me. Or like this. I will go here, and probably it will be better to explain with the pictures. For example, here in the stage 2, I mean, from the access point to the multiple responders, we can use a downlink of DMA, but it is one packet per each station, and it is just in one packet without any aggregation. So it is about just a payload and pass MACNO header, no aggregated MPDU or aggregated MSDU here. We just need to deliver a single packet to each station. So no aggregation here, or vice versa. Instead of a downlink of DMA here, we can aggregate them, use group cast address, and transmit it in wide bandwidth as a broadcast.
Okay, so you aggregate and use broadcast.
Yeah,
on the
a kind of. You cannot use groupcast or broadcast with aggregated MPDU according to the spec, because you should specify the addresses in aggregated MPDU subframe, and there are some issues with group or broadcast addresses here.
So, which is why you use AMSDU.
Yes, this is one of the reasons.
Okay, and you use AMSDU jointly with MIMA.
Yes.
Or two special streams, it only for the case of DMA, without aggregation of MSDUs.
Let me remember. I guess when we transmitting groupcast with aggregated MSDUs, we do not use any MIMA. I mean, we do not perform such a set of experiments, actually.
Okay, so this just means that on slide 12 you have a picture.
It is an station for you. You can look here, and then, for example, it is P2P. I mean, it is sent from the access point to the controller, but then the size of groupcast and this aggregated data is the same.
Oh, that's okay.
And I described this scenario as a P2P. I assume here that it is the stage 4 of my communication cycle.
Okay, thank you. No, I got it. Thanks.
I guess the question about MIMA during groupcast is rather complicated to consider. Okay, I hope this is close now. The next question from... Yeah.
So the next question from Artem Krasilov.
Yeah, I can read it. Do you consider frequency selectivity gain for retransmissions? The packet occupies the whole channel.
Maybe I can comment if you go to slide 18. So as far as I understood from your results, any additional retransmission does not provide you any gain in reliability. It seems to be very strange, because if you have at least frequency selectivity, you, for example, can select another channel, try to use another channel, and maybe the channel will be good for you, and you need to have some gain in reliability. So for me, it's strange why you don't have any gain at the second try.
Okay, then the first part of the answer is that in here we once again consider wide bandwidth. I mean, it is just a downlink P2P. So we use then whole bandwidth and for the retransmissions. The second part of the answer is that we did some additional checks for with OFDMA, I mean downlink of DMA or uplink of DMA, and because we cannot get any channel information, we should choose the new resource and unit for the retransmission randomly. So we are likely, because the channel is uncorrelated, we are unlikely to get into the same channel fate, because the correlation of the industrial channel is quite high. So, and probably if we if no some channel information will be available for us, yeah, for sure. For retransmission, we just use different MCSs and choose the different reuse or subchannels and so on. But unfortunately, it doesn't help at all in such a set of scenarios, because once again, the channel is highly correlated during the TXP
Yeah, you need
period,
to
let me
look
say.
into the profile of the channel in frequency, and what you are telling means that the channel is flat in frequency domain, which seems to be not the usual case for industrial scenarios.
I mean, for example, if we transmit and want to know many transmission within 18 RUs in 40 megahertz, yeah, and one of the RUs is extremely bad. I mean, it has SNR below 0, but the transmission fails, and we try to retransmit this one remaining packet in a wide bandwidth, yeah. But because of these small RUs with an extremely bad channel quality, we are unlikely to once again experience the same channel degradation. Why? Because we fail. Because we try to deliver such a packet in a wide bandwidth to save our channel occupation time. And because of effective SNR, the bad channel quality in a small RU will also drop the overall channel quality in a wider RUs.
Okay, if you talk about 18 RUs, 18 subchannels, this statement should be proven somehow, because it's not corresponds to my expectation of the real channels. So, okay, let us finish on this.
Okay. I hope I will manage to find our previous results and show you the case with OFDMA.
Thank you very much. That will be interesting.
Yeah, moving to the next question from Dmitry. Given your results, do you really need to standardize new mechanisms in 802.11 to improve the Wi-Fi performance or other RTAs? I guess moving to the last slide here, yeah. Probably we can still improve the situation significantly. And for example, if we address roaming issue, or if we address overhead on the sounding issue. So yeah, we still have a lot of new topics to work. Do you agree, Dmitry? Okay, I hope so. Moving to the
thank
next.
you. I think it's
Okay. Moving to the next question from Vyacheslav. Do you still have a Lyakhov? Yes, we have. Organized in such a manner that no jitter are produced. And for example, you can see in the pictures here some Lyakhov between stage 1 plus stage 2, then Lyakhov, then stage 3, and then stage 4. It is depicted here. And we allocate some free time to that the access point and will be able to count down the mean Lyakhov during this time interval. And because of this is our industrial controlled by us environment, we assume that there are no legacy stations that will be able to break our schedule. Let me see. And we can actually decrease AFSN to 0 because we can control the access points here. Yeah.
But my question is, why do you still have a backoff? So in your talk, you told us that DCA is we should disable DCA as much as possible, and you do this, but still you have some backoff. And my question is, why do you left this backoff? For which reason? If the network is fully controlled.
To be honest, there is no clear reason, but the impact from the backoff here, yeah, it is quite tiny in compared to the real occupied transmission time. So we can adjust and forget about it, I hope. The savings are quite limited compared to the overall cycle, the overall transmission time.
Okay, thank you.
Sorry for interruption. Related to the previous question, whether the need of the backoff is caused by the necessity to use legacy devices, so fully standardized devices, so you just cannot switch off backoff. You can change maybe its parameters, but you cannot switch it off completely.
Yet, but we can decrease AFSN to 1, I hope.
Maybe not to 1, but yeah.
To 1, yes, to 1, because it is access point, and 1 is the minimum value according to the spec.
Okay.
Moving to the next question from Artem. There is a lot of results for industrial floor scenarios in GPP technical reports. Do you consider them and unfair comparison should be done under similar scenarios and models? Regarding the second part, of course, I fully agree, but it is hard to done when you focus on the optimization of one technologies, and some reviewers will be required to perform the same set of optimizations for different plenty of technologies. So we just limit our comparison to the spectral efficiency, and that's all. Regarding technical reports, we refer to some of them. For example, our channel and models are based on the GPP technical report, but regarding evaluations, I hope not. But yeah, I refer to some really qualified and justified papers. I mean, even in the same transactions on Industrial Informatics journal. So I hope that the results which are referred in our paper are justified enough.
Okay, I just wanted to extend my comments that's making strong conclusion about superiority of the technology of one technology over another technology based on, let us say, a few papers which compare them in different scenarios under different conditions. It's quite strange. So I would not give such a strong conclusion that some technology is better than other technology for industrial IoT technology. So this is just my feeling of the situation.
Yes, of course, I fully agree and fully support this comment, and I shall avoid such wording. I'm sorry, but at least the researchers or the engineers that implement such industrial setup should consider the whole set of technologies, because and plenty of them and show then good performance results, and they then should then properly evaluate the scenario setup and then choose the best one.
Okay, agree.
Yeah, question from Vyacheslav. I will move to the slide 23. Yeah, go ahead.
Okay, thank you. I want to thank you for this picture. And from this picture, we can see that you, in your proposal, you mostly optimize stage 2 and stage 3, and the duration of stage 1 and stage 4 remains the same. My question is why you do not optimize stage 1 and stage 4, because the duration is small in the baseline, or we cannot do anything to improve the stage 1 and stage 4?
Okay, actually in stage 1 and on stage 4, a simple, an extremely simple P2P transmission. It's just in one frame of several kilobytes, and that's all. We actually can optimize these stages by using MIMA, because if I do my slides about MIMA, yeah, we can see that there are some gains in this type of stages. Stage 1 and stage 4. But for the simplicity, we decide to completely avoid MIMA and sounding, so we just keep these transmissions as a simple P2P. So in the picture, when we keep the same downlink MCSs, for example, we actually have nothing to optimize in these stages. So yeah, just transmit a frame of several kilobytes using MCS5. That's all. And then because of it, the duration of the stages keep nearly the same. For example, if you're looking here, it's just a data. Yeah, it's just a frame from one device to another, and we fix our MCSs. So we pretty much have no space to get some gain here. The only space is the MIMA, but once again, we decided for the simplicity of the whole system to discard it completely.
Okay, thanks. So, in fact, I have one more question. You show us the results for a particular scenario with access points which have inner cells of 20 meters width or something. As I understood, this scenario and placement of access points are given from some industrial partner. Do you try to optimize the placement of access point? So maybe it is better to have larger cells or smaller cells, but with bigger number of access points and so on.
Okay, actually, we have tried different combinations of geometry of the scenario, let me say, and actually, to be honest, the one that I show to you is different than one from the paper. Yeah, and during our projects, we tried to match some geometry in the setup, interreliability in the settings. For example, I do not keep the stations to the edge of the cell, which is unclear motivation. But when we switch into some square rooms, And so here probably the optimal placement for the access endpoints is rather clear. It should be placed in the center of the BSSs, and that's all. But yeah, I hope I answered.
No, my question is not. Maybe you need to reduce the BSS size or increase the BSS size.
I guess you should do that only when the range of the effective range of MCSs is not enough for you. Like for example, then when the cell is too high to deliver data even using MCS 0, or if then cell is too small. So on that you are able to achieve even 10 to the power of -6 reliability using MCS 11 from X. But in our cases, our optimal MCSs lies in a range of 5, maybe plus -2. So I don't see a clear motivation to do that, but for sure 20 meters is okay, and the range of the room is should consider together with the power of emission. Yeah, of course, and probably if we wanna speaking on different geometry setup, we should get some different power emission values, and we should build a different setup. But in our scenario and in the picture here, I guess the solution is pretty much simple. Just keep the MCSs in the range between 0 and 11, and that's all. I don't know, and quite a long sentence, but I hope you will get the main motivation here, that there are no things that can be optimized unless we change some power or distance significantly. For example, there is no difference between room of 15 meters or 20 meters. Yeah, that's all.
Okay, thank you. So, do we have any more questions from the audience? Okay, I guess that's all for today. Let me thank Anton for the interesting presentations, and also I want to thank Artem and Dmitry for interesting questions and discussion. See you at the next seminars. Goodbye.
Yeah, thanks a lot.